Um, so yeah, sorry, I'll repeat that. So an example of baseline differences is that Catholic school students have potential outcomes, different potential outcomes when they're not treated from the potential outcomes of Catholic public school students when they're not treated in the first place. So they do have different outcomes even before getting treated. So they Catholic school students have higher potential for SAT schools, higher SAT scores in the first place. So that way, they're having higher scores on average when people naively compare Catholic school students and public school students. This could be because of parental wealth or income or stuff like that, or they have higher interest in formal education and stuff like that. So there could be a lot of different reasons why there's baseline differences, but here my point is that even before getting treated, they do have different potential outcomes in the first place. Does that make sense? Or yeah. So that is reflected in the mathematical terms right here. For those who got treated, or the treated group, their potential outcomes, even before getting treated, it can be higher than this one. That is the baseline difference that we're trying to look at here. Good? Any questions? No? All right. And then let's talk more about how to link, how it works, how this difference between causation and association works out in regression lines. Okay, so it starts with the potential outcome framework. Yi is y0i plus y1i minus y0i. This is the potential outcome framework that we covered 10 minutes ago. And the first task is to make this framework look like a regression line or regression equation. How do you do that? Let's say EY0I. And so that way they're the same equations, right? Because it's adding one number and subtracting the exact same number. Good. The point here is that it can look like the grand mean or alpha here. Good. Does it make sense? And then this term is eta I, exactly, or error term for the regression. So this is the x variable, treatment variable, and then this is the beta coefficient, which is delta I, right? This is the effect size, right? And this is assumed to be delta because regression lines assume the same effect for all individuals. So you are adding assumption in the translation of this framework to regression line. Right? If you look at it, then alpha, delta multiplied by t and the error curve. It looks like a regression equation. Good? Yeah.
What is the second under y1i minus y0i? That's
Eta I. It should be this one.
that's the error.
Yeah, it's the error term. Yeah.
And the middle one is also just delta. Or?
Oh, this is delta regression coefficient or the effect size.
So we assume the beta coefficient is constant.
Right. Delta coefficient is constant. Yeah. In the good. Yeah.
Whereas the first delta is just delta.
Oh what?
So the first delta is just a delta. The second one is a delta regression coefficient.
So it was delta I, right? This delta I means the effect size, right? So, or the effect size.
Sorry, what is the first symbol that you wrote?
Oh, this one?
Yes.
Alpha. This is the grand mean of the regression line.
Okay.
Or the intercept. So it looks like a regression line, right? And we're trying to reach to make it comparable with the S, which is y1i given t1 minus this one, right? So naive estimator is potential outcome for the treat when they're treated for the treatment group, and then potential outcome of being controlled for the control group. Right? This is the naive comparison. The next task is to make this regression line comparable to the S right here. How would you do that? You would assume, condition this regression line on the treatment. Right. So you are conditioning yi on the yi one. And then put the expectation values on it. Expectation operations on it. Good. And alpha here is always alpha because it's a number. It really doesn't depend on anything, right? And then we assume that T1 is 1, Ti is 1, so it becomes 1, and delta is delta. And then there is expectation of eta I given T is 1. Does it make sense? So do you see what's going on here? So basically, you are assuming or conditioning the regression line on the treatment group, and then put the expectations operations on it. Question? Yeah.
So now we're trying to link S into a regression line. Like
Right, yeah.
Okay.
Yeah. And then if you do the same thing with the control group, Ti is 0, so it becomes 0. Eta I given Ti is 0. So what does that tell us? S would be the result of subtracting this part, subtracting this part from this part, right? So it would be delta plus expected value of eta I this matter is the causal effect plus the baseline difference. The error term is whether the error term differs depending on the treatment or when they're actually treated or not. Right? So if T and eta are independent from each other, then naive estimator would be causal effect because they would be same, right? Depending on T, this one does not change, right? Any questions? Yeah.
I'm just saying if we don't have the constant assumption, so the second equation, therefore
Mhm.
plus the
Delta?
Yeah, the delta.
Uh-huh.
So maybe the ATT, right?
Right, yes. I will
So-
cover that like right now actually. About when we don't assume effect when we allow effect heterogeneity.
I just think that assumptions, the constant assumptions is quite weird.
Right, yeah,
It's quite
that's
weird.
true. But in regression lines, that's what we assume for using regression lines. I agree with that.
Yeah.
That
It's
the
really-
assumption is pretty weird.
it's
Yes.
really confusing.
Yeah, it can be a little bit confusing. Yes. Yep. So what if we don't assume the effects are same for all observations? There could be some effect heterogeneity. For example, I'll give you an example of that. For example, so for Catholic school students, they may have chosen Catholic schools because they tend to respond very well with the Catholic school system. So the Catholic schools' effect in making their SAT scores higher is really strong for those who actually went to Catholic schools. Okay. But then if you think of a situation where you just put public school students into Catholic schools, would they be responding exactly the same way? It's probably not, because they chose to be in public schools, and then they might be not that really interested in the ways of Catholic schools, teachers, teaching, or something. Right? Does that make sense? So the same treatment's effect on the treatment group and the control group can be different in this case. So ATT and APC are different in this case. Good. So last spring I actually demonstrated how to decompose these biases, but I learned my lesson because they didn't like it. So I'll just post the process of bias decomposition on the course website. if when it's published. But for now, I'll just tell you what the outcome is. Okay, how bias is decomposed into the causal effects and the bias. And so basically, S here is decomposed into ATT plus oh shoot. This is 0. Plus baseline difference and 1 minus pi delta of so this is the ATT, average treatment effect, on the treatment group only. And this is baseline difference. And this is effect heterogeneity. Okay. So the delta, the causal effect, can differ depending on whether this person got actually treated or not, because they can respond really well with the treatment. Good. And pi is probability of being treated, and 1 minus pi is probability of being not treated. Good. And this part constitutes ACE. Good. Am I going too fast? Going too fast? Oh, okay. No?
So on the second line where it says 1 minus pi, that's a multiplication symbol.
Oh, what? Oh, not multiplication symbol. It's in this context, it was used as a probability of being treated.
Oh no, I guess I mean in the notation it says parentheses 1 minus pi. Is that times the exponent?
Oh, time, yeah.
Okay.
Yeah. So basically, when ATT, probability of not being treated, effect heterogeneity is ACE. If you think about it, if there's no person who got treated, then ATT is exactly the same as ACE, right? Because everybody got treated. Does that make sense?
Yeah.
Yeah. Okay. And then as this number goes up, then ACE, which is the average effect as a whole, is really driven by the control group's effect sizes, basically. Good. Awesome. Yeah. Yeah.
And so in the primary example, when you wrote E and then the bracket, like the error term, given that the different treatment effects, so that would only be, so the naive estimate comparison, that would only be unbiased if it was completely homogeneous, the effects of the different treatments in everyone.
Yes. In regression lines, all like effect heterogeneity are basically assumed away. Yeah. So that's why. All right. Any questions so far? Yeah.
Sorry.
No, no.
Where it says ATT plus probability t equals 0 times F.
Oh, sorry. Effect heterogeneity.
Oh, okay.
Sorry about that. Then
So I'm guessing the first terms should be the AT.
ATT actually.
Is that different than what's on the slide?
Okay.
It says this
Oh, what?
is S equals, the slide, it says S equals ATT plus baseline difference, and then S equals AC plus baseline
Oh,
difference.
sorry,
So we did
AC.
the opposite
Sorry
on
about
the
that.
board.
Yeah.
Yeah, this is.
Yeah.
Sorry about that. AC.
Okay.
Oops.
AC.
I meant it. ATT.
So S equals ACE plus baseline difference.
Right. Yeah. Oh. AC. Yep. This is AC. Yeah.
Right.
Notice that there is no given side, so AC makes sense. Yeah. Good. Any questions?
You said that of 3 things.
Uh-huh. What? This-
Combination of the first one.
This is AP. Yeah, AP. Yeah. Sorry about that. All right. All right. Let's work on an example to really try to clarify what I mean by that. By all of the example, all of the stuff that we covered. And so we're trying to look at how whether you got a college degree or not affect your wage